Namaskar. I am Dhyan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Uh, I discuss with you basis in the course of linear algebra. We learn about a vector space, also called a linear space, and the basis of linear space. Suppose S is a set of functions with the following property. If phi1 phi2 belongs to S, C1 phi1 plus C2 phi2 belongs to S for any two constants C1 C2, then the set S is called linear space of functions. If a linear space of functions S contains n functions phi1 phi2 dot phi n which are linearly independent, and every functions from S can be represented as a linear combinations of these functions phi1 phi2 dot phi n, then the set phi1 phi2 dot phi n is called a basis for the linear space S. The number n is called dimensions of S. For a given linear differential equation, L of y is equal to y raised to n plus a1 of x y raised to n minus 1 plus a2 of x y raised to n minus 1 dot plus n of x y is equal to 0. The collection of all solutions denoted by S of L of y is equal to 0 is a linear space. Every basis of S contains n linearly independent solutions, and therefore dimension of the solution space S is n. To check the linear independence of the functions phi1 phi2 dot phi n, we consider the wronskian's W of phi1 phi2 dot phi n. There is a relation between the linear independence of the functions and the wronskian W of phi1 phi2 dot phi n in chapter first. We in chapter differential equation with the constant coefficient. Therefore, we go towards the linear independence and wronskian. We have seen the for the differential equation L of y is equal to y1 raised to n plus a1 of x y raised to n minus 1 plus a2 of x y raised to n minus 2 plus dot plus a n y is equal to 0. There are n linearly independent solutions phi1 phi2 dot phi n satisfying the initial condition phi r raised to I minus 1 of x naught is equal to 1, phi r raised to I minus x naught, phi I raised to j minus 1 of x naught is equal to 0, j is not equal to I. These linearly independent solutions of a basis of solution space of L of y is equal to 0. Every solution of L of y is equal to 0 can be represented as linear combinations of these functions phi1 phi2 dot phi n. Theorem start. Let phi1 phi2 dot phi n be a solutions of L of y is equal to 0 on I satisfying the initial condition phi r raised to I minus 1 of x naught is equal to 1 and pi r raised to j minus 1 of x naught is equal to 0 for j is not equal to I and x naught belongs to I. If pi is any solutions of L of y is equal to 0 on I, then there are n constants c1 c2 dot cn such that phi is equal to c1 pi 1 plus c2 pi 2 plus dot 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 cn pi n. Let phi is any solutions of L of y is equal to 0 on I. Let pi of x naught is equal to alpha 1 pi dash of x naught is equal to alpha 2 dot dot pi double dash of x naught is equal to alpha 3 pi raised to n minus 1 of x naught is equal to alpha n for some constants n alpha 1 alpha 2 dot dot alpha n. Consider functions psi is equal to alpha 1 pi 1 plus alpha 2 pi 2 plus alpha 3 pi 3 dot 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 alpha n pi n. Since pi 1 pi 2 dot dot pi n are solutions of L of y is equal to 0, by superposition's principle, psi is also solutions of L of y is equal to 0, and clearly psi of x naught is equal to alpha 1 pi 1 of x naught plus alpha 2 pi 2 of x naught plus alpha 3 pi 3 of x naught plus dot 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 plus alpha n pi n of x naught is equal to alpha n. As pi 1 of x naught is equal to 1 and pi 1 of x naught is equal to 0 for I is equal to 2, 3, 4 dot 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 n. Psi dash of x naught is equal to alpha 1 pi 1 dash of x naught is equal to plus alpha 2 pi 2 dash of x naught plus alpha 3 pi 3 dash of x naught plus dot 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 plus alpha n pi n dash of x naught is equal to alpha 2. Since pi 1 dash of x naught is equal to 0, pi 2 dash of x naught is equal to 1, pi 3 dash of x naught is equal to 0, pi n dash of x naught is equal to 0, psi double dash of x naught is equal to alpha 1 pi 1 double dash of x naught plus alpha 2 pi 2 double dash of x naught plus alpha 3 pi 3 double dash of x naught plus dot 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 plus alpha n pi n double dash of x naught is equal to alpha 3. Since pi 1 triple dash of x naught is equal to 0, pi 1 triple dash double dash of x naught is equal to 1, pi 3 double dash of x naught is equal to 0, pi n double dash of x naught is equal to 0. In general, psi dash of x naught is equal to alpha I is equal to 3, 4 dot 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 n minus 1. Thus we see that psi of x naught is equal to alpha 1, psi dash of x naught is equal to alpha 2, psi double dash of x naught is equal to alpha 3 dot 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 psi raised to n minus 1 of x naught is equal to alpha n. Thus psi is the solutions of L of y is equal to 0 having the same initial condition at x naught as that of pi. By uniqueness theorem, we must have psi is equal to pi is equal to alpha 1 pi 1 plus alpha 2 pi 2 plus alpha 3 pi 3 plus dot 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 plus alpha n pi n. Thus every solution of L of y is equal to 0 can be uniquely represented as a linear combination of pi 1 pi 2 dot dot pi n. Since pi 1 pi 2 dot dot pi n are linearly independent solutions, their set pi 1 pi 2 dot dot pi n is a basis for the solution L of y is equal to 0. Recall the wronskian's functions pi 1 pi 2 dot dot pi n is defined as the determinant w of pi 1 pi 2 dot dot pi n, pi 1 pi 2 dot dot pi n, pi 1 dash pi 2 dash dot dot pi n dash, pi 1 double dash pi 2 double dash pi 3 double dash dot dot pi n double dash, pi 1 raised to n minus 1 pi 2 raised to n minus 1 dot dot pi n raised to n minus 1 is